Yay! Last lesson of the unit. This is actually section 6.6. Way to kick off the lesson with an error. Woohoo! This is Pyre style. Okay, polyprotic acids. This is really not that complicated. Polyprotic acids, polyprotic bases, poly meaning more than one. So monoprotic are only one acid or one hydrogen or one hydroxide. Monoprotic. Acids have only one hydrogen. Hydroiodic, hydrochloric, hydrobromic, hydrofluoric, hydrocyanic acids are all monoprotic acids. They only have one hydrogen to donate. That's it. That's all they have. Now, there are some acids that have more than one acid hydrogen, and it can react more than once. And so if we're looking for formulas, polyprotic acid is H subscript X, A, and these are what we call polyprotic acids. Okay? H2SO4, otherwise known as sulfuric acid, H3PO4, otherwise known as phosphoric acid. So let's look at them where we see that there's going to be less than a 50% chance of that reaction happening, less than 1% of that reaction happening, and less than 0% of that reaction happening. Let's look at phosphoric acid. So H3PO4 plus water. H3PO4 is going to be the proton donor, H3O plus, and we're left with two hydrogens in our solution. Then what we can do is we can look at taking H2PO4 and adding it to water. And this then becomes the proton donor. So we're going to get H3O plus. This loses one of the hydrogens, HPO4, 2 minus. Pay attention, the charge is changing. And then here, this reaction that actually doesn't happen at all, HPO4, 2 minus, where this is also the proton donor, we're going to get hydronium ion and phosphate ion. So remember, the charges change as we get rid of a hydrogen. So each of the resulting ions can react with additional water to make more hydronium ions, but they get more and more, or less and less, I guess is the better way to say it. They get more and more less reactive. A very awkward way of saying it. Polyprotic acids. We think that phosphoric acid is very acidic, but it's only the very first reaction that comes to light. And if we go to page 8 and 9 of our data tables, strong acids, and the whole rest of the book is a weak acid. And when we look for phosphoric acid, we look right here. Oh, I should bend it flat. Phosphoric acid, H3PO4, gives us aqueous hydrogen phosphate. And we see that it's not that far off. Here's nitric acid, which is a very strong acid. And then we have 1, 2, 3, 4 acids lower. So it's at the stronger end of a weak acid. And where do we find phosphoric acid? Phosphoric acid is the acid that I was talking about in Coke and Pepsi and root beer that give it that dark caramelly flavor. Okay, the first reaction is only 50% complete, so it's actually a weak acid and it has a pH that's higher than a strong acid at the same concentration. So here is hydrochloric acid at 0.1 moles per liter of hydrochloric acid. It's got a pH of 1. Here's phosphoric acid at the same concentration, has a pH of 1.7. And in our brains, we're thinking, oh my goodness, 1.7 is so far down on the scale, it's got to be a strong acid. No, because we have peptic acid in our stomach that helps digest and break down the protein fibers, and our stomach doesn't eat away at us. I mean, thanks to the mucus layer, but it doesn't eat away at us. And its pH is 2. So, phosphoric acid is acidic, but it's a weak acid. So, in general, we can say that polyprotic acids are weak acids. Whose reaction with water, I'm going to cheat and reaction like that, whose reaction with water decreases with each successive step, which means each step. So if we look at phosphoric acid, we go H3PO4 to H2PO4 minus, H2PO4 minus to HPO42 minus, HPO42 minus to PO43 minus. So those are what we call successive steps. Sulfuric acid, remember, just like the English language, there's always an exception to the rule. Sulfuric acid is a strong acid because its first reaction with water goes to completion. So it's the exception to the rule. Polyprotic bases have the same idea. So some bases, like what's this guy called? Oh yeah, he's called acetate. These are monoprotic bases because they can only take on one hydrogen, meaning they can react with water only once to produce hydroxide ions. So acetate and water react to give us acetic acid and a hydroxide ion. Now, we can look at carbonates, which is what this is. CO32 minus is a carbonate. We call these guys polyprotic bases because they can react more than once with water. Note, it can take on 2 hydrogens. So the first reaction where water now becomes the proton donor and carbonate becomes the proton acceptor. We get HCO3. Watch this, the charge changes just to a 1. So we go from 2 negative to 1 negative because we added this positive hydrogen in. And we get a hydroxide ion. We then take bicarbonate, or hydrogen carbonate, and we add another water molecule. Again, this becomes the proton donor, this becomes the proton acceptor, and we're going to get H2CO3 and OH negative. This guy is called carbonic acid. Makes our pops nice and bubbly. And this is our base indicator, base evidence. Okay, so carbonic acid and hydroxide. So in general, what can we say about polyprotic bases? Well, polyprotic bases are weak bases whose reaction with water decreases with each successive step. Seems like we've seen that definition before, only we called it polyprotic acids, are weak acids whose reaction with water decrease with each successive step. Evidence shows that a carbonate ion solution is less basic than a strong base at the same concentration. When we look here and we see that this is a strong acid, perchloric acid, hydriodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, nitric acid, we would think that we would go up and we would call these very basic things, but we don't. A very strong base is anything that typically reacts with anything in group 1 or group 2. So sodium ions, potassium, lithium, those are all strong bases. Group 2 ions actually fit more the definition of polyprotic bases because they have multiple not multiple charges. I don't mean more than one, like +3, +4, like iron, valence charges, but they have, I guess we could call them valence electrons. So barium is in the group 2 ions, and it's not a polyprotic base because you can't go and take barium hydroxide, split it apart through simple dissociation with water, and get barium and hydroxide, and then try and take the hydroxide and react it with water and get a lone HO product. I'm not even sure what you would get. Okay, so barium hydroxide will dissociate, meaning that it'll split apart into its cation and its anion. Remember, we have to have a balanced reaction. There's 2 hydroxides here. We'll make sure we have 2 on this side. Okay, and that's it. We can't do another successive step. We just said polyprotic bases are weak bases whose reaction with water decrease with each successive step. You have to have more than one step. This is done. One and done. Okay? So let's look at the homework part of it. This is the fun part. This is the part everybody enjoys. Lesson 2, you're going to go back, you're going to do questions 5 and 6 for bases. You're going to do questions 13 and 14 for the acids. You're going to look at part B. You're going to fill in the chart because you're highly intelligent people. And then you're going to go to the very last part of the workbook. You're going to work through three questions. 3. And you can do it. It's going to tie all of the pieces together. Remember, pH is equal to the negative log of the concentration of the hydronium ion, which means that POH is equal to the negative log of the hydroxide ion. The concentration of the hydronium ion can be found from 10 to the negative pH. Hydroxide ion can be found from 10 to the negative pOH. We're going to remember that we can figure out pH and pOH when we have the other piece of information because they both add up to 14. What are the other pieces of information that we need to remember? We need to remember simple dissociation versus a reaction with a hydronium or water molecule to produce that hydronium ion. We need to remember, we need to consider mole ratios between reactant and product. The product being the hydroxide ion or the hydronium ion. What are other things that we need to consider? Just really, I can't stress enough, really look at what you're paying attention to. If it says that the pH of sodium hydroxide is 13 and it asks you for the concentration of the hydroxide ion, don't use the scale. This is pH and hydronium ion. If we're looking for hydroxide, we can only work with this piece here. You'll have to figure out what POH is. You would have to go 14 minus 13, and we would get 1 for the POH, and then we could figure out the concentration of the hydroxide ion. So just, those are the pieces you really have to pay attention to. All right, stop the video, work on your questions. Have a great week.